You have already studied the fundamentals of chemical kinetics. That includes rate laws, different types of reactions like consecutive reactions, reversible reactions, and other methods how to determine the order of reaction. Now, one of the most important part of the chemical kinetics, that is theories of reaction rate. Now, it is a big concept, and from school level you are studying the most important fundamental theories of the reaction rate, that is called, you all know, the temperature dependence of rate constant, that is called the great Arrhenius equations. That is also one part of this theories of the reaction rate. And if you see our syllabi, although we have not included this Arrhenius equation, but I can tell you that this is the starting point of all these theories of the reaction rate. I will not explain the details derivation of this Arrhenius equation, but I will discuss some of the salient features of that Arrhenius equation and what is the need of studying these theories of the reaction rate. Why we study theories of the reaction rate. And today I will discuss only the fundamental aspects of the theory of the reaction rate. I will try to explain today the correlation between the Arrhenius equation and collision theory, which is in your course. And in first semester, you have to study up to absolute reaction rate theory, or sometimes it is called the transition state theory. And in second semester, there are other theories of the reaction rate, and that is applicable for unimolecular reactions. So that is the today's my agenda. Now you all know that this is a very common topic, and it is available most of the Indian as well as the foreign books. But I suggest my student that you must refer the Atkins physical chemistry, because I am using some of the derivation from that book. You can also refer this G.M. Barrow physical chemistry. That is also, that collision theory is very nicely explained in this Barrow. But suppose you want to learn much about these theories of the reaction rate, their history, their theories, so you should refer some of the specific books related to chemical kinetics, because you are all M.Sc first semester student. So I will request you to refer this very popular book and very simple book, that is Chemical Kinetics by K.J. Laidler. All the theories of reaction rates are available in this book. And in addition to that, because you know that day by day some progress is going on, and there are some good journals for the student as well as for the teacher, and one of the best journal for the student, that is called the Journal of Chemical Education. So if you refer this Journal of Chemical Education, you will get some of the recent information of these theories of the reaction rate. What is happened or what is happening after this Arrhenius equation, although it was discovered long back, 1889, and today is 2023. So if I see the technological development of theories of the reaction rate from 1889 to 2023. There are a lot of developments. Large number of Nobel laureates on this molecular reaction dynamics or the chemical kinetics, other things. So I will ask my student that you must refer this through online, this American Chemical Society publication, Journal of Chemical Education, as well as similarly for Royal Society of the Chemistry, another journals for the student as well as for the teacher, Chemistry Education, Research and Practice. And of course, there is also a very good journal, the Account of Chemical Research. So I have referred some of the articles related to these theories of the reaction rate. Now, as you know that whenever I start any topic, I must tell the student about the course content as per syllabus of that concerned university. We have already studied, so I will not discuss this part. Now I am concentrated only on this theory of the reaction rate. And of course, I have written these three important theories, but we will discuss the collision theory and then of course the transition state theory with respect to Arrhenius equation. Because if you understand this Arrhenius equation, you are able to write any equation without any problem. That is the thing. And then of course, I have already covered this kinetic salt effect. Next class I will cover the chain reaction. Don't worry about this. Today you will concentrate only on the theories of reaction rate. What does the actual meaning of these theories of the reaction rate? Similarly, when you enter in the second semester, because in this semester we will study up to absolute reaction rate theory, or sometimes it is called the transition state theory. But there is a lot of development after this transition state theory, and that is called theories of the unimolecular reaction. So don't worry about these things like Lindemann theory, Insolute theory, Rice, Ramsperger and Kallol theory, and ultimate theory of reaction rate. You must know the name at least. That is also very similar to the activated complex theory, or the transition state theory, proposed by a great scientist. Of course, his name is Marcus. He is also a Nobel laureate. Got the Nobel Prize for this electron transfer reaction. So that is called the RRKM theory. Rice, Ramsperger, Kallol and Marcus theory. Okay. So now I am coming to. Now if you see, it is very, very interesting, although as I told you many times that it is a school level chemistry. I think from class 8 or 9, everybody is well aware of the effect of temperature on the reaction rate. It's a very, very simple thing. But if you see this, you will feel some excited that it is a very long history. It is a very long history. Because everybody is well aware of this Arrhenius theory. You all know these things. That K, first point is that theories of the reaction rate means determination of rate constant. That is the first point. That means all the theory final equations should be started with rate constant. Clear? And what is the success of the theory? There must be a very good correlation between the experimentally observed rate constant derived from all those theory and theoretical values. There must be match between the observed rate constant, experimentally observed rate constant and theoretical rate constant. So every time you will see that there are three parts. I have already told you that long back. Maybe that time I also explained that E by KBT, Boltzmann constant and T. I have also explained you the different types of energy levels, and the population, which is very important. But if I write here, so there are three parts. Left hand side, this is the rate constant, and in middle, and extreme side, exponential term. So there are three parts. Exponential part, one is, if I have mathematicians, I should say it is a pre-exponential factor. Pre-exponential factor. Forget about this thing, whether it is a frequency factor, and or sometimes what happens if this value is 0, so the rate constant is exactly equal to that pre-exponential factor, or the, so don't worry about all these things. But if you see the whole story, it was started, a large number of scientists, after this PPT, I will show you a general history of this. Then you will realize that the contribution of kinetic theory of gases, contribution of statistical thermodynamics, contribution of quantum mechanics, all are involved in this simple effect of temperature on the reaction rate. So now that was started in 1885, long back, and then there was some problem. Everybody is well aware of this Arrhenius equation. But if I ask you what is the demerit or most important problem of Arrhenius theory, because this is the starting point. So in spite of tremendous application of the Arrhenius theory, because this is the first theory of kinetic theory, first theory of reaction rate, but in spite of large applications, Arrhenius is a Nobel laureate, but he could not explain actual meaning of A. He could not explain the actual meaning of A. 1889. Then two great scientists, one is from England, another is from the Germany, I think. One is Max Strauch, and another scientist is, I think, W.C. McLuhan. They, you see, 1889 and then 1916, you see the time gap. You see the time gap. They actually explain the actual meaning of A. So if I ask you, just if you understand the Arrhenius theory, you can very easily answer. Today I am not doing the derivation. I am just trying to correlate between all the theories. Now my next question is that, what is the formula of collision theory? So without any confusion, you must write, sir, it is exactly equal to Arrhenius equation. Only thing is that you must replace this A, which is frequency factor or pre-exponential factor or like that, and that is replaced by a new term, Z. What is Z? Z is actually number of effective collisions between two molecules per unit time per unit volume. That is actually collision number, or sometimes it is a collision rate. So that is replaced by this thing. So, but you know that there are some similar molecules, maybe nitrogen, N2, oxygen, but there may be a collision between carbon monoxide and oxygen. So sometimes the molecules is similar, sometimes molecules are dissimilar. And you know that there must be some proper orientation. There must be some proper orientation. So therefore, there are two types of collision theory. One is simple collision theory, another is the modified collision theory. So, and very simple, that the final formula, that is, there is no change in, it must not rate, actually we should write is that K. So K is equal to Z exponential minus, I will explain everything. So this part is same. I am not now discussing what is that part. I will explain. This part is same. Only thing is that there is change in A is replaced by the Z. I will explain what is the actual meaning of the Z. So derivation of collision theory is also very important. Now my last question is that again there are some problems. Of course, they have solved that problem that A can be replaced with the Z, because you know that for any type of chemical reactions, of course, we need some collisions, and of course effective collisions. But again, after at least 11 years, you see, so I always consider the history is just like 110 years. Why I am talking about all these things? This story of 110, because it was started in 1889, and in between there is 1986, a very important year, I will tell you why, and then 1999. I will explain what is the relationship between 189, then 1986, and then 1993. I think 5 Nobel laureates. 5. Yesterday, you all know that Chemistry Nobel Prize of 2023 has been announced, and 3 great scientists, because you know that we are all in our department, we are all working on these nanomaterials and quantum dots. And in physics also, I always consider the femtosecond spectroscopy, but now Nobel Prize is for 10 to the power minus 18, that is attosecond. In my last year also, I always discuss this 10 to the power 15 femtosecond and photosecond. So don't worry about all these things, but you must know. So after 11 years, there are some problems regarding this collision theory. And if I write a simple thing, A plus B, everywhere I write the same thing. You have already seen. This is the activated complex and product. So the structure of the activated complex, distribution of energy among the molecules, that is very important. You know that you increase the temperature, rate of reaction increases. You know that there must be some collisions, and some collisions are effective collisions, and you also know that a fraction of molecules having energy greater than the threshold energy. That day I just told you the energy level diagram, energy and the population, vibrational energy level, rotational energy level, translational energy level. So that fraction in this class, there are, I always give this example, that there are 60 students in this class. After the declaration of result, it will be possible for me that out of 60 students, suppose 55 students got above 75% marks. I will be very, very happy. That means the fraction of molecules having energy greater than the threshold energy. That is the thing. But how this energy is distributed, that is important. So 3 great scientists, I will show their photographs. Henry Eyring, Peljar, Wigner, Wynne-Jones, they actually derived this absolute reaction rate theory. My dear student, their nomenclature may be different. That means you can call it a transition state theory, because in between reactants and product there must be some transition state. In between reactants to product there must be some activated complex. So sometimes it is called transition state theory, sometimes it is called activated complex theory, but the most appropriate name is transition state theory. It is the most important theory. And if I ask you what is the formula of why I am saying that all these theories are interrelated. Now, if I want to write the final formula of absolute reaction rate theory, let me start with this. First is K A. I just want to first theory 1889. Then of course collision theory 1926 Max Strauss. Same K Z. Of course, you have to derive it. And derivation is, there are two derivations. If you are a good mathematics student, so you will understand the derivatives of the collision theory. And if I want to write the modified collision theory, because proper orientation is required, so we have to introduce a factor that is called the steric factor. So this is modified collision theory. And last theory as per your course. So don't forget. I hope that you will never forget in any interview or any, just if I ask you, write the formula of the collision theory, you are able to write. Similarly, last is that again absolute reaction rate theory, or the sometimes is called the transition state theory, is exactly, this part is same, this part is same. Problem is here everywhere, A or Z, and this part is common, fraction. So K is equal to KB is Boltzmann constant, not rate constant, T H, Planck constant. So again A is replaced by Z, Z is replaced by a terminology. This is absolute temperature, Boltzmann constant, Planck constant, exponential minus delta G and RT. So, of course, you can see it in the front line also. So, from today, you always remember that all these three absolute reaction rate theories and collision theory are almost, I am not saying, but if you see this time 1889 to 1935, you see the, and you all know that delta G, which is called free energy of activation. I will explain that what is the free energy of activation, is equal to enthalpy of activation, and very well known equation, you all know, this is called the Gibbs-Helmholtz equation. So a few minutes ago I told you that it is the contribution of kinetic theory of gases, contribution of thermodynamics, contribution of statistical mechanics, contribution of the quantum mechanics, which is very important for deriving these things. So I can write, I can use the red color so that you will find K is equal to KBT H, and if you just in place of delta G, if you write this, so exponential minus delta H by RT, exponential, because this is minus, so delta. Now question arises. So now it will be easy for you to remember all these things. Now question arises. that why I am talking about the statistical thermodynamics, why I am talking about the kinetic theory of gases. After the discovery of Arrhenius equation, although you all know that this equation is related to temperature dependence of the great equation RT square. I will show you this equation. One top. But if I want to learn, it is okay that we increase the temperature, but how do I study this part? Is here again it is common, this part is again it is common, this is also common. I will explain what is the difference between the energy of activation and free energy of activation. But all are exponential term, fraction of molecules. Out of 60 students, 55 students scored very good marks. Then you know that there are some active molecules, there are some passive molecules. In any chemical reactions, it is a very universal truth. It is absolutely impossible that all the 60 students secured more than 85% mark. Fine. So we have to understand that because there are 60 students, 60 molecules, you just consider you are all molecules and you are colliding. So I have to deduce or determine the number of molecules having energy greater than that threshold energy. So for that I have to calculate the total number of molecules. Suppose this is capital M, total number of molecules, or M0. After attending this 6 months course, the hardcore teaching of Dr. Indrapal, hardcore teaching of me or Dr. Manmohan, out of 60, 55 students are converted into excited state. And there is a very important statistic that is called the Maxwell-Boltzmann statistics, which is very important in chemistry or spectroscopy. Without knowing this, yes, with the help of this Max, I will show you that formula. So this is the story of, therefore today I am just talking about the genesis of theories of the reaction rate. It is not so simple that K is equal to A by RT. So we need the help of this statistic. And another important thing is that is you all know, I think you have studied in your B.Sc classes, B.Sc first year physics, Maxwell-Boltzmann distribution of molecular velocities, because all the molecules are having different velocities or the speeds, but we have to calculate that how many molecules possess a certain amount of velocity. Then of course I can predict, yes, this type of thing. So friends, there are two theories are responsible for this collision theory. One is kinetic theory of gases, another is the statistical thermodynamics, and both the theories were developed by two great scientists. You all know the name. One is J. Clerk Maxwell, another is the Boltzmann. So now I am coming to again this. So this is the story. Now sometimes what happens, students get confused regarding the derivation of. Therefore I just always request you to refer some of the good books like Atkins or Levine or Albert Daniels or even Chemical Kinetics by Laidler, because large number of scientists were worked, but so there are two types of derivations. One is proposed by the Wine, Jones and Eyring, and another derivation is proposed by I ring, Evans and Polanyi. I'll explain the things, what are the derivation. But what is our objective? Our objective is that to know the concentration of this activated complex. And it is very simple. That means if I want to write A plus B is equal to activated complex, so K is equal to, you all know this thing, X A and B, right? So if I want to determine the X, it is K A and B. So I must know the correlation between K and constant. I will explain when I will teach the activated complex theory or the transition state theory. I think now you understand the story of these theories of the reaction rate. And second point is that all the theories are almost similar. K, again I am just repeating, K is equal to A exponential E by RT, first part. Collision theory, K is equal to Z. Third, in place of Z, we write some KVTH, and in place of E, we use the delta G activated, that means free energy of activation. Again, I am just giving the whole because I am a physical chemist and I have done a lot of work on the chemical kinetics, so I have a special affinity for the chemical kinetics of the thermodynamics. So therefore, I always refer the story of all these theories. And please, so you see that there are thermodynamics is also there, kinetic is also there, statistical mechanics also there, and there are a large number of scientists: Eyring, Polanyi, Wynne-Jones, Max Strauss, W.C. McLeod, Hinshelwood, and even if you see this simple Arrhenius theory, lot of scientists, and most important contribution is the Van 't Hoff, because the Arrhenius theory was determined with the help of Van 't Hoff equation, that is temperature dependence of the equilibrium constant. And equilibrium constant is composed of rate constant. So that Van 't Hoff equation can be splitted into two equations, and with that equation we determine these equations. Now, I always give the credit of this Arrhenius equation to these three great scientists, because from 1862 to 1889, they studied different types of chemical reactions at different temperatures. I always consider that Arrhenius equation is an empirical relation. Why it is called empirical relation? Because on the basis of the results of various scientists, Arrhenius concluded that everywhere, if I increase the temperature 10 degrees centigrade or 5 degrees centigrade or 20 degrees centigrade, rate of reaction increases. And the first reaction they have studied, you all know that KMnO4 and oxalic acid reaction is very common. So they have studied in different temperatures. Similarly, hydrogen peroxide and HI reaction. So credit goes to this Van 't Hoff as well as the Arrhenius. This is actually Arrhenius. He got Nobel Prize in 1903. And he is the first Nobel laureate of our chemistry. First Nobel laureate. Van 't Hoff. And of course, Harcourt also contributed a lot. Now, always remember, although they have not awarded the Nobel Prize, but they are the great scientists, because they actually discovered and solved the problem of the Arrhenius equation, problem of the collision equation, and ultimately that they actually determined the transition state theory. So I always consider them, they are the great transition state theory. And out of these three, this is the great gentleman. You see that they have just blackboard. This is K. You see K. and this is K, rate constant is kBT, and this is the H, and of course there are some rate, and this is the Michael-Polanyi. And why I am just saying, again I am saying 1889, 1986 and 1999, because although we studied all the things, we know the temperature effect, we know the collisions, we know the delta G, delta H, delta S, but what is happening in the molecular level? I think in second semester you will study molecular reaction dynamics. Molecular reaction dynamics. And his son, he is Michael-Polanyi. He is Michael-Polanyi, but his son, John Polanyi, along with two other scientists, T.S. Lee and Herzberg, they were awarded Nobel Prize in 1986, which you will study in the second semester, continuation of that absolute reaction rate theory, the molecular reaction dynamics. And then again there was a problem. So I must salute another great scientist, M.Sc. I'll show the photographs. And he actually discovered the transition state. You might have heard about different spectroscopy, but M.Sc. got Nobel Prize in 1996. So therefore I always correlate Arrhenius to M.Sc. 110 years journey, that is called the transition state spectroscopy, TSS, transition state spectroscopy, or sometimes it is called the femtosecond. And this year Nobel Prize in the physics, femtosecond means 10 to the power minus 15. You can understand, 10 to the power minus 15, 10 to the power minus 15. And now we are talking of the attosecond, 10 to the power 18. So again, this is the great, and without this theory, we can't determine this equation. And you know that always if I consider, again I am talking about the same thing, A plus B is equal to C plus D, or what is the product, and if it is K1 and it is K inverse 1, so simple derivation, you just call it d by dt of natural log of K1 or minus 4. This is equal to, if you can, it is internal energy. You can write the delta E also. I am not discussing the what is actually activation energy. Today I am not discussing the activation energy and other things. So that is, we can write like that. See? So it is, if it is, so E1 by RT like that, RT square. And for second case also same thing. So credit goes to the Van 't Hoff for the determination of, so d by dt natural log K inverse 1 is equal to E inverse 1 minus RT square. And you know that if I just integrate it, RT minus 1, so I will get this natural log of K minus E by RT plus one constant. You all know this is a p-exponential factor. So K is equal to, but we will not study these things. So credit goes to this Van 't Hoff. Van 't Hoff. And as you know that, you see the large number of research is also going on, and if you see the title of this article, that reaction rate theory, what it was, where is it today, and where it is going, femtosecond. So hernias to femtosecond, and they have given all these, I think, large number. 1935, this is the original research paper, 1935. Wigner and Pelgier, and hernias also published this paper in 1889. You see. So therefore, I always excited to tell you the story of this, what it was, what is today, and where you are going. In second semester, you will study the femtosecond and other things. And this is my most favorite transparency, and I always try to correlate all these things. 1889, again, I must salute this great man. So what is the mission or the message of just the take-home message is that although we are not studying today the details of the Arrhenius equation, we are studying from the school level. But again and again I am telling why I am telling the school level. But now you will realize the importance of this great man, because without the knowledge of Arrhenius equation we can't do anything. Whether it is a RRKM theory, another Nobel lecture, Nobel Prize, and again, as I told you that John Polanyi, the student or the son of that Michael Polanyi, long back, they discovered the transition state theory. Polanyi, Evans, and Henry Eyring. But in 1986, with the help of infrared chemoluminescence and cross molecular beam method, in second semester you will study all these things. They Herzberg, USA, still Polanyi is also working. T.S. Lee, Taiwan, and this John Polanyi, they got Nobel Prize for the molecular reaction dynamics of the chemical elementary process. And 1999, the great scientist, although he is no more, his name is Ahmed Zuel, although he is from the Egypt, but he was working at California Institute of Technology. And I have read large number of research papers of this Ahmed Zuel, and this Polanyi is work with this Ahmed Zuel. So you see the relationship between the starting point, Michael Polanyi, John Polanyi, and then that is the actual story of this whole theories of the reaction rate. So again, I told you that I will discuss the collision theory, and then I will discuss the modified collision theory as per your course, and then I will discuss the transition state theory. This is our agenda. But today I will not derive anything. And again, I am just for the student. Sometimes this is a transmission state coefficient, but you can understand these things. The same thing again. Same thing, and again this part is there, and this part is fraction. That is very important part. So therefore, we need, how do we calculate these things? Yes, we have to take the Maxwell-Boltzmann statistics. So before I end, I will just my last transparency, because today I will not discuss the whole thing. There are some, as I told you, that it is also for Journal of Chemical Education. Journal of Chemical Education. You see, I think in 1982. And the origin and status of the art, still people are remembering him. And I show you that d by dt of, you see. And 1985, J.J. Hood, another one top and other things. Is all this, you see the temperature range. Here you see the temperature range. 10 to 30 degree, 32 degree, 1 to 40, 25 to 55, 80 to 130, like that. Now, same thing, you know that, because that was not visible. So what I have just elaborated, same thing, so that you can understand that how and the data considered by the hernia, as I told you. So therefore, it is an empirical relationship, and ultimately he derived this energy of activation. Energy required for the reaction minus energy possessed by a particular system. And all collisions are efficient, I have already told you. Most important, a short question, that what is the demerits of Arrhenius equation? That is the frequency factor. So last, the link between the quantum mechanics and this is the two great scientists. So nobody will tell you the story behind this Arrhenius equation and collision equation is that Boltzmann distribution, and second is the Maxwell-Boltzmann distribution of molecular velocities. You see, this is actually fraction of molecules. So if I plot a graph between this fraction of molecules and energy, this is speed, or you need not to view it is suppose T1. Again we increase the temperature T2. Again we increase the temperature T3. So the number of molecules having energy greater than threshold energy, T2 will increase, T3 will increase. So this is the reason for this explanation. How this energy is distributed over the molecules. And this is the last point. You can use the capital N also. N means actual molecule excited is equal to N0 exponential minus delta E upon kBT. Same thing. So now you can understand that all things are related. It is related to fraction of molecules. Again, if I write K is equal to A E by RT. So how do I know this fraction? By this method. That means N dash, N0, there is energy difference. So thank you very much. Today I will just discuss these things. So from next class I will discuss all these things, Max-Taussian collision theory and others. So today again, just as I summarize it, that I will not derive today the collision theory or absolute reaction theory. Today I am just giving a glimpses of this genesis or the origin of theories of the reaction rate. From next class, Saturday, I will discuss the derivation of collision theory. Thank you very much.